Section 3.6 is about proving theorems about perpendicular lines. The first theorem says if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So here's some vocabulary that maybe we haven't seen in a while. It says linear pair. So remember, a linear pair is two angles that are adjacent to each other, meaning they share a side, that are forming a straight line. So it says if two lines intersect to form a linear pair, so like here we have line H cut by line G, and angles 1 and 2 are formed, so angles 1 and 2 are the linear pair, and it says if those angles of the linear pair are congruent, that meant that the two lines must be perpendicular. So if angle 1 is congruent to angle 2 and they're a linear pair, then angle 1 and angle 2 are right angles, meaning that G is perpendicular to H, just like it states. The next theorem is actually very blatant. It's something that you probably already assume. It says if two lines are perpendicular, then they intersect to form four right angles. So the theorem stated in terms of the diagram says if A is perpendicular to B, so line A perpendicular to line B, so A and B, then angles 1, 2, 3, and 4 are right angles. So not just one of them is right angle, all four of them are right angles. And the next couple of examples will be just applying these theorems. Example number 1. In the diagram, line AB is perpendicular to line BC. What can you conclude about angle 1 and angle 2? If line AB is perpendicular to line BC, so AB is perpendicular to line BC, so that's this entire line. We could have also called it line DC. What can I conclude about angles 1 and 2? So to mark up this diagram, if AB is perpendicular to BC, I know that's a right angle. I also know that every angle formed by the two lines intersecting are right angles. That means that angle 1 and angle 2 are both right angles. I also know that angle 1 and angle 2 are a linear pair since they are forming this straight line. So we have a linear pair that is forming a straight line, so that means that this line is perpendicular to this line, so that means that angle 1 is also congruent to angle 2. Since we know all right angles are congruent, and that is all I can conclude about angles 1 and 2. Example number 2. Angle 1 and angle 2 are congruent. What can you conclude about the measure of angle 2? So this is applying that first theorem that we talked about. Angle 1 and angle 2 are a linear pair. We are told that angle 1 is congruent to angle 2. So I'm going to mark that on the diagram. Angle 1 is congruent to angle 2. I have a linear pair that is forming two congruent angles. Therefore, according to that first theorem, I know that angle 2 must have been 90 degrees because that would mean line A is perpendicular to line B. So therefore, what can I conclude about the measure of angle 2? I can conclude that the measure of angle 2 is 90 degrees. Since again, I have a pair of congruent angles that are a linear pair, that means they're forming the straight line, which is 180 degrees. So if these two angles are congruent, that means that they have to both be 90 degrees, since 90 plus 90 would equal the 180. Next, we have another theorem. It states if two sides of two adjacent acute angles are perpendicular. So remember, adjacent angles are angles that share a side. So if they're saying the two sides of two adjacent acute angles are perpendicular, so basically that just means that this ray is perpendicular to this ray, then the angles are complementary. This makes sense because if this line is perpendicular to this line, they're forming a right angle. Therefore, the two angles, angles 1 and 2, have to add up to 90 degrees because, again, a right angle is formed. And if two angles add up to 90 degrees, they are complementary. Example number 3 has us doing another proof. The given is that ray ED is perpendicular to ray EF, and they want us to prove that angles 7 and 8 are complementary. So basically, we are just proving that last theorem, that if two angles that are adjacent, sitting next to each other, their sides that are not shared are perpendicular to each other, that means that the two angles must have been complementary. So remember, the first step in a proof is to state your given. So we were given that ray ED is perpendicular to ray EF, and our reason is that it's given. Based off of that information, I should know that this angle is a right angle as it is marked in the diagram. So I know that angle DEF is a right angle. And I know this because of the definition of perpendicular lines. Since I knew that these two rays were perpendicular, I knew that the angle was a right angle because of the definition of perpendicular lines. Our next statement was that the measure of angle DEF is equal to 90 degrees. I know this because I stated that it was a right angle. Because it was a right angle, I know that it was 90 degrees. So my reason would be the definition of a right angle. So again, that is my reason. A definition of a right angle was the reason I knew that the measure of angle DEF was 90 degrees because again, just in the step before it, I stated that DEF is a right angle. Our next reason actually does not tie together these up here as it normally does. It states that the measure of angle 7 plus the measure of angle 8 is equal to the measure of angle DEF. So measure of angle 7 plus the measure of angle 8. So 7 plus 8 is equal to the big angle DF. So here I see two smaller angles that I'm adding together and getting the big angle. That is a postulate. Back in chapter 1, we talked about the angle addition postulate. And again, it states that two smaller angles added together can give me that bigger angle. So my reason is the angle addition postulate. Now I can look at these two statements together. I see that the measure of angle DEF is equal to 90 degrees, and I see that the measure of angle 7 plus the measure of angle 8 is equal to the measure of angle DEF. So I have two things, the 90 degrees and the measure of angle 7 plus the measure of angle 8. They are both equal to the measure of angle DEF. Therefore, I would know that the measure of angle 7 plus the measure of angle 8 is equal to 90 degrees because of the transitive property. And our last statement states that angle 7 and angle 8 are complementary. Just in the previous step above it, I said the measure of angle 7 plus the measure of angle 8 is equal to 90 degrees. I know that if two angles add up to get 90 degrees, that means they're complementary. So my reason for statement 6 would be the definition of complementary angles. And that's it. Now I've proven our previous theorem that stated that if two lines, or in this case two rays, are perpendicular to each other, then the two angles that are being formed are complementary. Next we have two more theorems. The first is the perpendicular transversal theorem. It states if a transversal is perpendicular to one of two parallel lines, so you see in this diagram we have line H and line K that are parallel because they're marked with the little triangles, and the transversal J is perpendicular to line H, then it is perpendicular to the other. So if line J is perpendicular to line H, then it is also perpendicular to line K. We could prove this using the corresponding angle postulate. Since I know that line H and K are parallel, I know that corresponding angles are congruent. Therefore, if line J is perpendicular to line H, that means that this angle here is a right angle. If this angle is a right angle, its corresponding angle would be a right angle. So the corresponding angle would be this one right here. So I would mark that with a little box. So that would mean that line J is also perpendicular to line K, which is exactly what this theorem states. The next theorem is kind of the reversal or the converse of the perpendicular transversal theorem. It is the lines perpendicular to a transversal theorem. It states in a plane, if two lines are perpendicular to the same line, so here we have line M and line N that are both perpendicular to line P, then they are parallel. So the two lines that were perpendicular are parallel to each other. So that would mean that line M and line N are parallel. And it's exactly what this states. It says if M is perpendicular to P and if N is perpendicular to P, as it states here, then line M is parallel to line N, just like it shows here. This again can be proven using the corresponding angle postulate. If line M is perpendicular to P, it forms a right angle right here. If line N is perpendicular to P, a right angle is formed right here. These two angles would be corresponding. We know due to the corresponding angle postulate converse, that if I have corresponding angles that are congruent, then the two lines are parallel, which is exactly what this theorem is stating. Example number 4, determine which other lines, if any, must be perpendicular. Explain your reasoning. So first off, we are shown that line C is perpendicular to line B. So what we're being asked is there any other pair of lines that are also perpendicular? So to start, I see that I have an angle of 75 degrees here and an angle of 75 degrees here. If I put line A on top of line B, these two angles would be on top of each other, and therefore they would be corresponding. If I have corresponding angles that are congruent, like I do here, that would prove that line A is parallel to line B. So that's what I'm going to write first. So again, I just stated that line A is parallel to line B, and I justified it by stating that the corresponding angles are congruent. I'm going to also mark that line A is parallel to line B on my diagram, just as a visual to remind me that A and B are parallel. As you remember, little triangles are the symbols you use to mark that two lines are parallel in a diagram. So now that I know that line A is parallel to line B, I now see that line B is perpendicular to line C. I had a theorem on the previous slide that stated that if a transversal is perpendicular to one of two parallel lines like we do here, then that transversal is also perpendicular to the other parallel line. So therefore I can conclude now that line C must be perpendicular to line A. So I know that there's a little box here to indicate that on my diagram. So again, I can conclude that line C is perpendicular to line A based on that theorem on the previous slide. So that's what I ended my problem with. I stated that therefore C is perpendicular to A because of the perpendicular transversal theorem, which again was the name of the theorem that stated if I have a transversal that is perpendicular to one of two parallel lines, then it is also perpendicular to the other parallel line. Next, we have a couple of vocabulary words, or really they're phrases. So the first phrase is the distance from a point to a line is the length of the perpendicular segment from the point to the line. So in the diagram that I provided, we have point A, and if we want to find the distance between point A and line K, we would just drop a perpendicular line down, straight down to line K, and then we would just find the distance between those 2 points. So again, the distance from a point to a line is the length of the perpendicular segment between the point and the line. The next phrase is the distance between two parallel lines is the length of any perpendicular segment joining the two lines. So by looking at this diagram, I have line M and line P that are parallel because they're marked as such. And if I want to find the distance between those two parallel lines, I'm just going to drop a perpendicular line down from one line to the other, and I would just find the length between those 2 points. So I would find the length of segment CD or EF, but again, it has to be the perpendicular distance between those two lines. You wouldn't want to go like diagonal because you're not taking the quickest route between the two lines, which again, the quickest route would be the perpendicular line. Example number 5, what is the distance between the two parallel sides of this tabletop? So first, by looking at this diagram, you might assume which two sides are parallel, but we first need to prove which two sides are parallel. So what I'm going to do is just use rise over run to find the slope of each of the 4 sides. So looking at this first line here, I'm going to count up and over to find the slope of that. So if I start here, I'm counting up 1, 2, 3, and over 1, 2, 3, 4. So the slope of that line is 3 over 4. Now on to the next side of the table, this line right here. I'm going to pick out 2 points on it so that I can count the slope. I'm going to pick out that point right there, and I'm going to count down 1 and over 1. So the slope of that side would be -1, since I went down 1 and over 1. Finding the slope of this line down here, I have 2 points, and I'm going to count up and over. So I'm starting here and counting up 1, 2, 3, and over 1, 2, 3, 4. So automatically we see now that the top side here is parallel with this side here because they both have a slope of 3 over 4. But let's just verify that this side doesn't have a slope of -1 like this side did. So I'm going to pick out 2 points. So here's a point right here. So I'm going to start at the 0, 3 and count down 1, 2, 3, 4, and over 1. So the slope of that line is negative 4 over 1, or just negative 4. So it looks like these two sides are the parallel sides. So again, the question was, what is the distance between the two parallel sides of this tabletop? So we need to find the perpendicular distance, because remember in that last theorem, we know the distance between two parallel lines is a perpendicular line between those two sides. So if the slope of this line is 3 over 4, the slope of a line that's perpendicular to it would be negative 4 over 3. So let's just start at one of the points and let's count down 1, 2, 3, 4, and over 1, 2, 3. So it's actually this point 3, negative 1. So let's draw that line in there just so we have the visual. And what we want to do now is find the distance between the 0, 3 and the 3, negative 1. So we have to go all the way back to the first chapter when we did the distance formula. That's the one with the big square root. It looks like this. Distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So remember, the two ordered pairs that we are using are 0, 3 and 3, negative 1. And we're just going to put that into the formula. So I would have the square root of, subtract the x's, 0 minus 3 squared, plus subtract the y's, 3 minus negative 1 squared. Now remember, the last thing you're going to do is take the square root. So I'm going to do what's inside the parentheses first. 0 minus 3 is negative 3, and negative 3 squared is 9, plus 3 plus positive 1 is 4, and 4 squared is 16. 9 plus 16 is 25, and the square root of 25 is 5. So the distance between those two parallel sides of the tabletop is 5 units. And that's it for this section. Make sure you write down all of the theorems, and don't just name them using the numbers they named the theorems with. Actually name them with the titles that they gave them. Again, make sure you write down all of the theorems so that you can refer to them on a test or a quiz if you're asked to justify an answer, or if you're asked to complete a proof. Make sure you write down all of the theorems with their given names, not the numbers they were assigned. Not like theorem 3.9 or whatever it is for these theorems. Make sure you jot down anything that you don't understand or questions that you have so that we can cover that before we move on, and then we'll see you then.